Thank you to have me here. I'm quite honored that I can present before a lot of experts here this topic. And I have acoustic emission. Probably some of you already using this type of technology in your tests, several types of tests, scratch test, indentation, impulse test. In simplest case scenario, it can be used as another tool for a scratch test detection, the first crack. But today I will persuade you that it has much deeper use. Some theory. Acoustic emission is a phenomenon of acoustic waves, radiation in solids that occurs when a material undergoes irreversible changes in its internal structure. That can be some dynamic reconstruction of material structure, some plastic deformation, dislocation movement, or some cracks which are much more hearable. Because actually it's a sound. It's a sound just not hearable by a human ear. It's just sound detectable by some electronic elements. You have some mechanical loading that creates some structural changes, and the small displacement is somehow detected by different types of sensors. In practice, this is how it's done. In macro scale, you have some volume, probably pipelines or something similar, and you have some sensors, and acoustic waves is received by the sensors, acoustic waves created probably by some crack, and the sensors convert it into voltage, which is amplified and further processed. You can have even triangulation where it happened, so it is important. It can give you amplitude, it can give you time, it can give you direction where it happened. The company we have worked with is a Dakel, a Czech-based company, which use it as a non-destructive testing method for integrity of pressure vessels, and their main job is integrity of pipelines in nuclear reactors. So it's very important, let's say, technology for our safety in Czech Republic. They are cooperating with Czech Republic and Slovakia plants, not only the big plants, nuclear plants, but also other types of less developed plants. So what was our modification? To create sensors with a lower noise, higher sensitivity, and easy to use. My point is make sensor which is applicable to any environment. We are using it with micromaterials nanotest, P3, but it can be used as a standalone, it can be used in any other system. This is how the final product looks like, patented and created by the company along with us and tested. If you want to analyze the acoustic emission during some local mechanical tests, you generally have two approaches. You attach sensor close to the object, close to the sample with some glue or something, or you can attach the acoustic sensor to indenter, because you want to be as close as possible to source of acoustic emission. Because thing is that acoustic signal can be dampened during the process, through much of, let's say, interfaces between the source and the sensor. But we have this product which is, let's say, quite handled, because it's a normal holder and not much more bigger, or even it's smaller than standard micromaterials holder. It's a little more thicker, and we are using it quite often. We are using it nearly on every measurement as a standard tool. Applicating wax, high temperature, heating it, applicating wax, and attaching our own samples. So sample can be detached, can be used further. This is how it looks like, the holder. This is how it looks like in the combination of P3 system. There's some cable, and you can ask, okay, but it's a big bulky thing. Maybe it's dampening the signal. It can, but not so much. This is our probably the biggest sample we have measured. Some metallic stuff like 2 centimeters, and some titanium nitride coating, chromium nitrides, titanium nitride coating combined. So actually there is several interfaces. This is like 4 multi-layers. Now the quite thick metal and the wax, then the metallic part, and the sensor is inside. And these are the results. As Ben told yesterday about multipass wear tests, so several tests in subcritical load, scratching and checking when something happens. It's like, let's say, speed up wear test or something like that. So in the first scratch, we had it's these samples. So in the first scratch, we had a nice signal from the first plowing, because there is much more contact with coating itself, tip with the coating, and then there is less contact because it's already plastically deformed. So, and you see in the fourth loaded scratch, something happened. So we can see there is a deterioration of the coating, which again is increased in every other step. So it's not that something happened here and nothing is happening here, but it's still on the same spot, a little more broken and cracking and something like that. So our philosophy is to do a continuous recording during all experiments and hit detection. I will explain what I mean by this later. It can create a large amount of data, so we kind of wanted to handle this stuff because it can create after one day like nearly hundreds of gigabytes, which is not easy to handle. So what we have did is to take the signal from nanotest itself. It can give you a signal, and we are using it as a starting point and closing point. So then we have just a very specific measurement during just the test. We are using here are some electronic parameters, mainly things, sampling frequency, 10 megahertz, it's changeable, and the bandwidth, 50 kilohertz to 1500 kilohertz, because we want just the important thing, just the acoustic emission from the material, not noise around. So we need to cut it. And definitely we need some amplification. This is how the whole system looks like. A holder, cable, and just a unit that takes the data, and computer. Some more technicalities. Most important is that we are using piezoelectric element inside, zirconite titanate. We have used several types. It was a part of our research. We had one big, one segmented, two smaller. So we tried a lot. Actually we have like 10 holders, little different. So when we have some measurements, what we are doing, we are just using for one project, one holder to not mix the results. But we have elements with different sensitivities. Generally, in practice, you can use capacitive transducers, laser interferometers, but we are using this approach, piezoelectric element. Definitely, we need to preamplify it to have some reasonable data. And very important is shielding. We are using coaxial cables with higher grade. Once, there was a guy with Samsung S7 Galaxy mobile phone. He just came to our laboratory and we had super signal from acoustic emission. I don't know why. And no other mobile had done it. I have done experiments, but yeah, this has done it. So we need some shielding, which is very important. Okay, so let's check some results. In the, let's say, simplest case scenario, it can be used as a method, is another method for a scratch test. This is a typical topography, scratch topography, progressive load scratch test. Here we have initial topography, just scanning the surface, loaded scratch, where something beginning to happen here, and final topography that sends the rough surface. You can see here, okay, it's nicely aligned. We can use these two methods, or we can use acoustic emission, nicely aligned. So you would say, okay, why I would need it? I have this information here, but as you can see, we can use it as a standalone. You don't have time for look using microscope. It takes time, so you can use just depth change from the micromaterial system itself, or you can use acoustic emission. As you notice in the first picture, where I have several of these acoustic emissions records, so we can, in our software, we can place like tens, more it would be not so much visible, but several acoustic signals, several acoustic records, and just to compare it at one moment. So it's quite quick. But in most cases, acoustic emission detects failure earlier. these are several coatings. I will show more of these tests. It was my dissertation thesis, silicon carbide, annealed with 600, 900 vacuum in air, and acoustic emission tends to be quickest. What it means, it was just one type of critical load, the first cracking occurrence, but acoustic emission tends to be quickest in the detection, which means somehow we didn't see through visibility, through microscope image, like what really happening. This is how it looks like in advanced mode, because what I showed you until now is this, just a record of acoustic emission signal. We call it envelope, because actually this bit is created by one hit. There is a signal, something happens, and there is a signal, and this is the signal in 250 microseconds. So this is how a hit looks like, and the hit is perceived as a one line, but you can see they can be coupled together. But you have information not about just this, but even about hit, and this hit is specified. You have some amplitude level, amplitude threshold, you have some let's say length of the hit, that and everything is set up so you can take out some bad hits you don't like. You can just set up what you need to detect. So some small hits can be taken out, or you can make it more sensitive. We have some accounts, which is something like hit, but it's just a amplitude threshold, and this counts how much thresholds were surpassed. And we can also do spectrum analysis of the hit itself. We hope there is some information in this. So okay, let's look again at two more tricky scratch tests. Here you can see maximalized scratch test, silicon carbon nitride annealed after 900 degrees. You would access, probably there's a critical load, something here. We have used confocal imaging, and maybe you would say, okay, it's here. But actually, not far away, it was a little away, it was here. Because acoustic emission just, I would say, heard it sooner. As I said, it was part of my dissertation, so I did a lot of work on it. And we have used, let's say, digging using focus and beam. So focus and beam ions were cutting into the samples, created a cross-section. And we have noticed that on the very beginning, there is some interface cracks, which didn't went up to the surface. So nothing could be, in that point, visible on surface. Also not in the depth change record, because this not change the depth rapidly. At the latest part, there's a big cracking going up to the surface, but from the cross-section it looks so nice. So in this moment, it helped move it a little, because you want to see or detect critical load, first critical load. This is it, not this. So it can be helpful in more ductile coating. Let's say brittle coating would break instantly. You would have it in a microscopic image, you would have it in depth change, but more ductile can be detectable preferably by acoustic emission. Or adhesion failure. What is a scratch test? Oh, it's not adhesion test. We would like to have it as an adhesion test, but you can, with combination of other method or a lot of experience and one instrumental help, detect it as a pure adhesion failure. Because if you don't see it on surface, it can be the adhesion failure. I will show you several more tricky scratch tests. Here you can see, okay, if you will try a lot and magnify it a lot, there are some cracks which can be visible from the depth change. You can say, okay, maybe I don't, but nicely detectable with acoustic emission, no question here. You could say, okay, I can handle it with depth change record because I'm experienced or microscopic image, but I bet you didn't see this one. There are some 3 small little cracks that probably, again, is some subsurface cracking. And as they are nicely aligned with some frequency, it's probably real data, not a noise or something. Also, I have it in my 2 articles, so if you want, make a photo and read it more. There are several more of these scratch tracks, like this one, again, a little more tricky. nothing happening here. So from visual observation, no data. Only cracking visible on surface was here at the end. Acoustic emission nicely detects this crack, or no, this some cracking. From depth change record, okay, maybe if you would be bold enough, you would say, I can see because there is a change of the slope. It is, it correlates, but you need to be bold to say this. But I try to find something more difficult. Another crack, silicon carbonitride, 900 in vacuum, because for just some results, because Tomáštík talked about several annealing approaches and analyzing silicon carbide, which will be definitely used in as a future electronic, which is already used in Czech Republic. We have company onsemi semiconductors that are creating silicon carbide's chips because they need to survive in cars. And it's not about bits, it's about watts. It's so much energy, and they heats up a lot. They can handle it because they said silicon carbide is heat resistant. But apparent, what I did during my dissertation, silicon carbides get too brittle. But silicon carbonitride, not so much. Through our results, silicon carbonitride prevail in the scratch test, mostly because some oxidation layer, let's say triple layer, created on surface. So it was just some results. But let's get back to acoustic emission. Visually, nothing happening here. In vacuum, there is no triple layer, so we were looking at what will happen. In depth change, I don't know, like I would be brave enough to say something happening here, but acoustic emission heard this. So again, these articles you can find there. And if you want several more of these scratches and images, I have it in my dissertation here, so I can give you like 2 hours of reading. This is my favorite. I like it. It's my fairy tale. Because from microscopic observation or depth change, you would have bad information. Let's see what's happened. We have a scratch track, progressive loaded, and let's see depth change. In first topography scan, we have nice surface, and there is something, some debris. Okay, so let's go to unload scratch, increasing load, but not so much here. I would expect something will be here, but just a little bump. But in acoustic emission, there's a signal. A little later, and if you see here, microscopic image, there is something, surface cracking apparently, but no depth change, but acoustic emission hears that. And then we have like gross spalling, destruction. And if you would be experienced user of scratch tester, so you could say, okay, there's a backward spalling, something like that, because it looks like that. So you would guess, okay, in that moment something happened and backwards part. So critical load is not this, it's probably this. But because of backward spalling, this substrate cracking revealed, you wouldn't see it otherwise. This is one scratch track from, let's say, 10, and this is like 2 cases happened, and other 8 cases didn't happen, this backward spallation. So I didn't even know about substrate cracking. But here you can see, so what happened actually? There was some debris, braked, and then the spallation occurred from that point backwards because the final topography sees the spallated or delaminated substrate. So this is what happened. Actually, the critical load, first critical load occurred in this moment where is a substrate cracking. And you can also use the advanced method to analyze the heat, shape, and spectra. So this is what can be helpful. And more cracks, 2 quite rough scratch tests that cannot be distinguishable using visual observation and depth change record, but acoustic emission gave some differences. There are more signal in chromium nitride than in the second sample. Some concrete, only port-lined face of a concrete gave some acoustic emission, others not. Okay, I promise even some non-scratch tests. So here are some indentation. In indentation, you have loading phase, dwell phase, and unloading phase. And what you would expect, most cracking happen in loading phase. But there are even some cases in creep or dwell phase. Going to theory, what is happening? This is a glass cracking. During loading, you have radial cracks. And during unloading, you can have lateral cracks but sometimes radial, which is like lateral connection to the surface. So this is what can happen. In this K10 glass, we have this thing happening. What we have did was to use several more glasses, because our department is a department of optics. We generally create some optical instruments, telescope. So we just wanted to test how brittle they are, how they can crack, because these telescopes are there in the open. So this what happened, several different types of cracking of several different glasses, and acoustic emission. So you can see there are a lot of differences. This glass, it's actually created an acoustic burst and a lot of acoustic emission during unloading. So probably the lateral cracking, and here also. So it can give you nice information, even if it doesn't look like so much distinguishable. Let's say these are, but several times we have made the measurement for Sisemek, Turkish big company that creates something like Gorilla Glass. Sisemek, I don't know, I forgot. So we also tested this Gorilla Glass. So let's say one last image from me from indentation. This is let's advanced type of output that we can have from our system. It's actually 3D graph. We have indentation, some cracking in the loaded phase, none in creep and none in unload phase. And what you can see here is like time record, whole of the test. So okay, from here to here. Frequency, so it's a spectrogram. We analyzed each hit and have a frequency, and the color means counts in that frequency. So you can see these hits like in this spectrum. I don't think it's much scientific record. It's more like nice record that can be placed to some publication. I just prefer the standard and frequency. We also tested it in impact test. You would guess, okay, impact test, too much loud, too much sound around. But we had some differences in comparison to alumina and PCZ sample. I probably forgot what is it. It's in the book of Tomáštík and Winbeek. There is everything, I forget. So we can have differences even in this impact test. Okay, so what's next? Actually, this is a slide, quite old, from my predecessor, my colleague Radim Svetlik, who is not in our department anymore. And nothing changed from these past 2 years, because actually we didn't have so much people focusing on this topic. We are using as a standard tool our acoustic emission for scratch test, indentation, for impulse test. But we are planning to use it mainly with using AI, because we think there's a lot of information hidden inside. The Goldilocks thing would be to find coating, like cohesive cracking and adhesion cracking of coating from a substrate, and somehow find it in the data, in the spectra, in the hit shape. So this is what we plan to do if there will be some more people. So maybe if you have some nice students and you want to send them to some practice, we are open to take them to this research. In future, we plan to buy in situ indenter, and we will look probably on these nanopillars, micro objects testing with acoustic emission. So we will see how it will look like. So at the end, acoustic emission is a powerful tool, standalone tool, or in combination as a multiple sensor approach. That can be used for different types of coating. No, for all of them, very ductile samples cannot be measured, because ductile samples cannot do acoustic emission, but it can give you mainly subsurface, damaged subsurface information, which is definitely important one for surface and local mechanical properties. And at the end, I would like to thank Tomáštík and Ben Beek that I'm part of their book, because multi-sensing approach and the acoustic emission, some part that you have seen in this presentation, is written in this book as a one chapter. So definitely buy the book or obtain it somehow. Thank you.